Welcome back to Serious Dynamic Programming. Today we're going to see how to use the functional equation to identify the optimal policy. My name is Phil, and as always, the slides are available on GitHub. So, for identifying the optimal policy, we're going to proceed as last time. First, we're going to see a necessary condition, then look at, what we need to make it sufficient. In the end, we're also going to see an example. We're really interested in solving dynamic optimization problems. And in the last video, we saw how to use the functional equation to identify the true value function. And the true value function said was the solution to the dynamic optimization problem. With the true value function, I'd now be able to tell you how much the field should be worth to you or how much you should be willing to pay for it. We also said that the value function was very important because it allowed us to trade in the infinite number of constraints for something we can actually work with, and which now gave us some grip on the problem. But as a farmer, what you really want me to be able to tell you is how much you should plant today, the day after, the day after that. That is, what is the true policy, what is the true optimal policy. So how do we get that? Actually, if you paid close attention in the last video, in the last proof, we actually did have something to say about this. So let's jump back into it. If you remember, we made a guess at the value function, said, well, for whatever starting value you're given, the value of the problem is simply 2k. And well, if this is, we know that if this candidate is a true value function, it must satisfy the functional equation. So we have that for our starting value k0, let's maximize, we'll choose an optimal k1 feasible from k0. And because utility is linear, this maximize 2k0 minus k1 plus 1/3, which is the discounting, plus our candidate, which is 2k1. And we saw that this is linear in k1 because this reduces to -1, 1/3 k1. Because we can't borrow, k1 needs to be greater or equal to 0. So this is actually, because this is decreasing k1, this is optimal for k1 equals 0. And so this is our optimal policy, consuming everything today, not leaving anything for tomorrow. And how do we know that k1 equals 0 really is the optimal policy? Because we saw that our candidate really is the true value function. And with our policy, k1 equals 0, we actually do achieve the result of the value function, which is the maximum feasible. So this gives us a very intuitive necessary condition for what it means to be the optimal policy. And Shirky and Lucas call this theorem 4, and they say that, well, if a path is optimal, then it does achieve the maximum feasible value. It does achieve the value of the value function. You may ask why this only gives us a necessary condition. Well, for the same reason as in the last video. If you remember, we said that if we have a function which maps from any point of the domain to infinity, well, the functional equation is trivially satisfied. Well, and because it's a similar reason, we're also going to need a similar sufficient condition as in the last video. And this is what Stokes and Lucas call theorem 5. They say that if a candidate path, which is a different name for policy, is feasible and satisfies theorem 4, i.e. it does achieve the maximum feasible value, which is the value that the true value function gives us, and it satisfies some growth condition, then this path is really optimal. But just look out here, the growth condition is a little bit different. It's the lim-su condition, which is more general than the simple limit and always exists. And now this doesn't have to hold for all feasible paths, but only for the candidate path. So yeah, let's prove it. Now, from the last video, you remember that what we want to show is that this would indeed be the least upper bound to our problem. But actually, we already know that the functional equation is, per definition, the upper bound of the sequence problem. So you don't have to show both ways, you only have to show one way, also one way. So what we want to show is that this what we have to show is that is weakly smaller than the sequence problem. Because if it's weakly smaller and weakly larger, it actually needs to achieve the sequence problem directly. So again, we're going to start off with the function equation. So we have that with the optimal path. So from a starting value, this is exactly equal to, because it satisfies theorem 4, we can now immediately jump to saying that this is exactly equal to f x star y star plus beta y star. And actually, let's not call this y, but immediately say that this is t x t plus 1, and this is also xt plus 1. So now, as in last videos, we can use the same trick and basically reverse the expansion we saw last video. So this is, again, as you remember, xt plus 1 plus beta f xt plus 1 x star xt plus 2 plus beta squared value function of x. So we can keep doing this, and you remember that if we do this n times, this will be excuse me, oh, that was too much. Well, from 0 to n minus 1, beta f xt x t plus 1 plus, and here this is, as before, n plus 1 v x t plus n plus 1 and, no, excuse me, n plus 1. And now with our, if we now apply our lim sup condition, we know that this is actually weakly smaller than the lim sup of term A. So this is term A and this is term B plus lim sup of B. And this is just a very fundamental result of what the lim sup condition is. You can sort of think about this as, well, if you have two graphs which are of different phasing, so this would be the limit supremum, and this could, for example, be the limit supremum, that this is small, that the sum is smaller than the limit of both parts added. Well, excuse me, this would be the limit inferior. Now, but we said that this tends to 0. So this would be simply the limit supremum of our sequence problem, and hence we've shown that the t is weakly smaller than the sequence problem, which is what we wanted to show. Now let's look at an example. The example here is very similar to the previous video. It's again conquering with linear utility, but now we have production which is equal to the inverse of our discounting. As in the last video, we're going to make a assumption of the we need to guess at the value function, and we're going to guess that this is again the identity, so that for k naught this is equal to 3 k naught. Now, this must satisfy the functional equation. So we have that for k naught, this equal to the maximum k1 feasible from k naught. And so this is linear, so we have 3k naught minus k1 plus 1/3 times our guess, which is 3k1. And now, if we look at this, this actually becomes 3k naught minus k1 plus k1, which is the same as simply 3k naught. We see that this actually is independent of k1. So what k1 we choose doesn't actually matter. So k1 is any k1 greater or equal 0 is optimal. Now, does our theorem 3 hold, which we said was that the limit of beta v and our candidate is small equals 0. Now, well, this doesn't hold because we can say that the upper bound of our kt is 3 to the power t k naught. So the limit of 1 over 3 to the power of t is simply the limit of 1 to the power of t k naught, which is certainly not 0 for k naught unequal to 0. And so the sufficient condition doesn't hold. But if we look at this problem, well, of course it doesn't hold because we are basically as patient or impatient as our production. And so, but looking at this problem, we do actually know that this is the true value function. This is the maximum value we can achieve. But so what's our optimal policy here? And well, we say we have theorem 4, but we know that theorem 4 holds for any value k1 which is greater equals 0. But is there maybe a little bit more we can say about the what constitutes an optimal policy? Well, theorem 5 was the lim-sup condition, which said that the limit supremum for t going to infinity of our discounting the true value function must be, well, no, excuse me, this is not k naught, and our candidate path must be smaller or equal to 0. Now, knowing what our candidate function is, we can translate this to limit supremum of 3 over 3 to the power of t kt, and which must be smaller or equal to 0. Now, from this it turns out, well, turns out that actually any consumption path that says this condition is optimal because it's a sufficient condition, and well, this is only optimal if we don't postpone infinitely long. So we can either consume everything today, that would be optimal, consuming the day after, everything that would be optimal, but we have to consume at some point. As long as we don't postpone consumption forever, this will be optimal. And I think this is a very interesting example because, well, the sufficient condition of the value function theorem 3 doesn't apply, but we can still make out, well, we can still learn something interesting about what optimal behavior would look like. So stay tuned and I'll see you in the next video.